interested in a little AC math theory, we are going to go through a couple of things here. You should have this handout. It's about 18 pages long, and I have developed this over a period of probably about 7 or 8 years. And this is a condensed version really of all the AC math you need, or all the trig and so forth you need in order to understand the calculations and computations you're going to have to do for AC electronics. And going along with that handout on theory, this is the theory handout. Going along with that, we have a worksheet. Now then, as usual, the numbers in the worksheets change with every printing of a worksheet, but the problems remain the same. So once you've mastered these math principles, then you should be able to handle any math that comes your way with respect to AC electronics. Now, the first thing, I've got this divided into 5 parts just to make it a little bit easier to keep up with. The first part has to do with the J operator and its use in AC electronics calculations. The values are the quantities X sub L and X sub C, which stands for inductive reactance and capacitive reactance. We'll talk more about that in just a little bit. We'll learn how to do polar to rectangular conversions and rectangular to polar conversions. And when we represent impedances, that is opposition to current flow, that a AC circuit has, then we can represent those things in either polar form or rectangular form. And we'll find it easier to do certain mathematical operations in one, and other mathematical operations will be easier in the other form. So it's nice to be able to convert back and forth. Okay, the first thing we want to talk about is the J operator and what it represents in AC electronics. There are 2 other passive components that you need to be aware of right now besides the resistor. The first of those is a capacitor. And that is the symbol for a capacitor. A capacitor is nothing more than 2 electrical conductive plates with a insulating material in between, or a dielectric. And this is the schematic symbol for a capacitor. We'll also be concerned with an inductor, which is nothing more than a coil of wire. And you will talk about how that operates in your studies of AC fundamentals. However, right now what we're going to say is that, you know, like we had resistance, and when we had a DC source and a resistor, we had a certain amount of current flow, and the amount of current that we had flow into the circuit was directly proportional to the voltage that we had applied and inversely proportional to the opposition to current that we had. Now then, that opposition to current that we had in DC electronics was referred to as resistance. And it is actually due to friction that's taking place at the molecular or the atomic level. And actually the molecular opposition gives rise to heat dissipation, and we have some power dissipated by a resistive opposition to current. Now, that is not true when we come to inductors and capacitors. If I put a capacitor in that DC circuit, after a certain period of time that the voltage is applied, the current in that circuit will equal 0 amps, because what have we done? We've put in an insulating material here. However, before current stops flowing, some current will initially flow, and the electrons will build up on this side of that capacitor, and they'll be taken away from this side, and so we'll end up with plates on either side that are charged, and we can store this charge. I can take that capacitor out of that circuit and it will remain charged until I dissipate that charge, or until I put a path for conduction, let's say around there, and let that charge leak off. If I apply an AC signal or an AC voltage source, an alternating source to that capacitor, we will alternately build up charges in that polarity, and then on the negative swing we will build them up in the other polarity. So we do have a net current flowing in one direction on the positive half cycle, and on the negative half cycle we have current flowing in the opposite direction. However, there is on the average some stored charge in that capacitor. If I had a stored charge minus to plus and I reverse the polarity, this is also going to be acting as a source and opposing that applied voltage. So we have some opposition to current flow in here that is due to the stored charge on the capacitor. That opposition to current that is due to the stored electrostatic charge on the capacitor is referred to as X sub C, or capacitive. Reactance. Capacitive reactance. Okay? Capacitive reactance. Okay, now then, its units of measure are ohms. However, it does not dissipate any power, because the opposition to current is not due to friction, it's due to stored energy in the form of an electrostatic field. The same thing is pretty much true of an inductor, only with an inductor, if we put current through this inductor, we have magnetic fields built up around this. The magnetic fields represent stored energy in the form of an electromagnetic field. If I take the current away, those fields will collapse and induce a current and a voltage in the opposite direction. And that sure also would oppose a changing voltage applied to that, just like it did with a capacitor. The opposition to current that an inductor has for AC is X sub L. That is known as inductive reactance. And again, it's called reactance instead of resistance because it is due to stored energy and not due to friction. Now, if I combine an inductor and a resistor in an AC circuit, I now have an R and an X sub L. And instead, I can't totally call it resistance, I can't totally call it reactance. I have to have another term. I say that the opposition to current that this circuit presents to a source is referred to as impedance. Okay, impedance. And it's got units of ohms. Ohms are the units. And it has an angle associated with it. And we represent it like we call Z for impedance. And the same thing would be true if I come over here and replace this inductor with a capacitor. I now have an X sub C associated with that resistance, and we still have an impedance situation as opposed to a pure resistance. And we're going to talk about this just a little bit further, and I might go ahead and show you how to calculate capacitive reactance and inductive reactance. I think since you've had your algebra and so forth, and some of you have already had some trig, this will be a pretty easy thing to do. X sub c is always calculated as 2 pi times the frequency of the AC signal, 2 pi f c, and then take the reciprocal of that. So let's just move this x sub c up here. X sub c is the reciprocal of 2 pi fc. Okay. Now, x sub l is pretty much the same formula, except you don't take the reciprocal. You simply substitute an L everywhere you have a C. So x sub L will be equal to 2 pi f L, the value of the inductor in henries. Whereas this is the value of the capacitor in farads. Okay, now then, when we plot these things on a graph, and graphs are very useful in AC electronics because they allow us to actually visualize what's going on. If I go ahead and plot an XY axis, normally I would refer to this as the x-axis and this is the y-axis. Now then, I'm going to change that. I am going to refer to this as the plus J-axis. I guess you were wondering when I was going to get around to this J operator I've been talking about. And this is going to be my resistance axis. Now, there are two ways that I can represent impedances on this diagram. Number one, I can just simply have a point in a plane out here, and I can represent it as R, out so many units of R, and up so many units of J. Like that. I can represent it that way. What are we talking about with the J? We're talking about the amount of inductive or capacitive reactance. On the plus J axis, we're talking about X sub L. On the minus J axis, we're going to talk about X sub C. Okay, we can also plot voltages and current on this graph using the J operator, but we're going to hold off on that right now and just do the impedance. The other way I can represent this point is to take a vector that's pointing to that point through a certain angle theta. And a positive angle is counterclockwise. So I can represent this point two different ways. I could say this point right here is R, radius, length of, remember that could be a circle. We talked about that unit circle thing. It's no longer the unit circle necessarily, but it is, we're talking about rotating a vector around a circle. So that would be R at some angle theta. It could also be R plus J X sub L. And that's the way I would write it in rectangular form. And this is the way I would write it in polar form. So those are the two forms, rectangular and polar, that we talked about just a little bit earlier. Now, there is always, let's draw a circuit associated with this thing. Here is a resistor and an inductor, and I'm applying an AC signal to this circuit. This is R and this is X sub L. I was given, say, the value of the inductor, and so I plugged that into the 2 pi FL formula, and I came up with X sub L. I had X sub L of 1, 2, 3, 4, 5, let's say maybe 5 millihenry by 5 ohms. And I had a resistance of 1, 2, 3, 4 ohms. And so That was the point in the plane where the two come together. Okay, so this vector here represents the impedance of this circuit. So we could call this Z, and we could call this Z. Okay, so we have Z at some angle theta in polar form, opposition to current that the source would see looking into that circuit, or we could have the Z in rectangular form. Now, it's not very easy to multiply and divide in rectangular form. It is not very easy to add and subtract in polar form. Therefore, we are going to use rectangular form for addition and subtraction when we need it, and we're going to use polar form for multiplication and division when we need it. All we have to do when we use polar form for multiplication and division is multiply or divide the magnitudes, which would be the impedance part, and then simply add or subtract. Add if you're multiplying, or subtract if you're dividing the angles. When we add and subtract in polar form, we add in rectangular form, we add R's to R's and J's to J's. So it turns out to be very, very simple, as you will see. All right, you will find an explanation of this these exact calculations on page 4 of the AC Math theory, handout on theory. And what we're doing here is we are looking, I didn't draw the picture of the circuit in the handout, but I've drawn it on the chalkboard here. We've got an AC RL circuit where we have a resistance value of 9 ohms, and we have an opposition to current that the inductor is presenting, an X sub L, of 18 ohms. What I'm interested in is doing the graphical and the mathematical operations necessary to look at this in both rectangular and polar form. Okay, my graph over here shows me a vector in the positive 90-degree direction of plus J. I have an X sub L value of 18 units. Now, I made this out of proportion, so I'm going to fix that right now. 18 units in the X sub L direction, and I've got a R value of 9 ohms. And I want to write the expression for this in rectangular form. Rectangular form, that terminology is used because we can dot in a rectangle here. We're looking really at this point right here, this point in the plane. And that point in the plane represents Z total for this circuit, the total impedance that the source sees. And that would be 9 plus J 18. Okay? 9 plus J 18. So that's the value of this point in the XY plane, or the RJ, R plus J plane. All right. Now I know that seems a little strange to you, but just go with it because it's going to make sense. And the more you work with it, the more sense and the more natural and normal it will feel. So that's the impedance of the circuit. If I ask you what the resistance of a circuit was that had 10 ohms of pure resistance in it, you would say it's got a value of 10 ohms. Our total is 10 ohms. Well, here we've got resistance and inductive reactance, so we have to say impedance because that's the combination of the two. Impedance implies always you have a mixture of reactance and resistance. All right, so my rectangular form is Z total is equal to 9 plus J18. Now, I would like to convert that into a polar form. All right, well, look at this. I know that I'm going to have a vector going from the origin out to that point in the plane, and that's going to represent my impedance in polar form. And that impedance vector is the hypotenuse of a right triangle. Now, we just got through going over the basic trig functions, so you should be familiar with this. If you are not, or you need a refresher, be sure you go back and watch the tape right before this, basic trig functions. Here's my right angle. Here is the angle of reference. I'm going to have a positive rotation of some number of degrees, and when I write this thing out in polar form, that's what's going to go right here. And my impedance, the length of that vector, is what's going to go right there. So now look, I can find the magnitude quite easily, can't I? Because I have this opposite side out here, and we already know that since we've got a rectangle, this side and this side are the same. So this is 18 units long. And this side here, he's 9 units long. Okay? So all I've got to do is use old Pythagoras. Pythagoras would say that z squared is equal to r squared plus x sub L squared, wouldn't it? So what do I need to do? I need to take the square root of both sides, and so I get z is equal to the square root of r squared plus x sub L squared. Now, you should be able to do that mathematics. When you do that, you get that z is equal to 20.12 units long. So this is 20.12. So my z total in polar form, the magnitude portion is going to be 20.12. Well, now what I like here is the angle, isn't it? All right, let's find a way to get that. Does anybody remember what the tangent of theta would be? The tangent of theta would be the sine divided by the cosine, the ratio of those two sides. So tan theta is equal to 18 divided by 9, which is equal to 2. So the tangent of that angle, whatever it is 2. Now, do you remember also we talked about the inverse tangent function, which is the angle whose tangent is. So if I say theta is equal to the angle whose tangent is 2, then I go to my trusty calculator, and depending on the calculator that you have, you put the value 2 in, and then you take the arctan or the inverse tangent. And when I do that, I got invalid data, so we know I did something wrong. Whoops, I have made a mistake here. I'm going to go back and fix it. Okay, this is good for you. I just realized what I did is I hit the arc cosine. I didn't have my glasses on, and I hit arc cosine instead of arc tangent when I was using my calculator here. So, everything I set up to this point was correct, and I simply put in the 2, and I hit the arc tan, and I get a value of 63.43 degrees for theta. So that's what goes in here where the question mark was. Now then, I want to really impress something on you here, upon you, is that we can never just simply say that the impedance is 20.12 ohms. We always have to say it's 20.12 ohms at an angle of 63.4 or 63.43, whatever that works out to be. Now, this is taken care of in your text, in your handout here. So there shouldn't be any problem with you being able to go back and go through it. I even use these exact numbers. So you should take care of that. Now, that was a rectangular to polar conversion. What if we started out and for some reason we already had the polar form? What would you do to convert back? Well, what we would be looking for would be the 9 and the 18. So the first thing we could do is we would also know the angle, okay? We're looking for this one, and we're looking for this one. And we've got an angle of 63.43. And we also know the magnitude, the 20.12. So I know that this adjacent side here is related to the cosine. So what I can do is I can take the cosine of theta, let's say R will be equal to the cosine of theta times the value of the hypotenuse, which is Z. So when I do that, you should put this in your calculator, take the cosine of 63.43 degrees and multiply times 20.12, and you will get an R of 8.99, which is close enough to 9 for our purposes. In order to find this side here, this side would be the sine of theta multiplied times Z total, which would be 0.849 times the 20.12. And that would give you a side of 18 inches. Okay? So in order to go back, you can do it that way. Now then, almost all of these calculators that we get nowadays have an automatic polar rectangular and rectangular to polar conversion function in them. I would love for you to be able to do this the long way so that you understand the mathematics of it, and so that if you get a wrong answer, you will recognize it as being wrong. Probably be a good thing for me to write that up. That says P-O-L-A-R. Okay, we've got our rectangular and polar forms represented there. Okay, on your worksheet, you have several places here. You have actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 chances to practice rectangular to polar, 5 rectangular to polar, and 5 polar to rectangular conversions. And as usual, the answers are in the back. You don't have to round off but 2 places. In fact, that's the preference. But you should be able to use your calculator to get those. I don't want you doing those necessarily by hand. I want you to become proficient at using your calculator to do those calculations. And if you have your book, you can look in your manual that came with your calculator, and I'm not going to try to explain that on this tape because there are different ways to do it on different calculators. If you can't figure out how to do it from reading your calculator manual, or you don't have the manual anymore, come to one of us and we will figure it out on your calculator and show you how to do it. The rest of this section, part 1, on the J operator and polar rectangular, rectangular polar conversion, has to do with another example using a capacitor as opposed to an inductor. And the difference is that the capacitive reactance, X sub C, could still be 18 ohms, okay? But the capacitive reactance would be plotted on the minus J operator. So we would have a minus J18 here. We would still have our 9 units of resistance. We'd still have a rectangle, only our vector would point here, and we would end up with a negative 63.43 degrees. Everything else would remain the same. The whole process is the same. But it's very important that the J operator is a negative J now instead of a positive J. And if I wrote it out in rectangular form for a capacitive circuit, I would say Z total is equal to R minus J X sub C. Or in this case, it would be 9 minus J $18. By the way, let's just mention that thing, that J, for a minute. If you're a mathematician and you're interested in knowing where that comes from, then you can look in math books and find out about the J operator. They call it, in a pure mathematics book though, they would refer to it as I, which is the square root of -1, which is an imaginary number. But we use it in electronics to designate a 90-degree rotation. Plus J for positive 90, minus J for negative 90-degree rotation. So this concludes our discussion on part 1. Okay, the next section is involved with the unit of measurement called the radian, and how that relates to degrees, and the different forms of the sinusoidal function and what they mean and how we can deal with those. So first thing I want to talk to you a little bit about is the radian. The radian, we have degrees, radians, and gradians as units of measurement, of angular measurement, units of angular measurement. So the one you're most familiar with, I'm sure, is the degree. However, in electronics, we have a lot of applications for using the radian. Now, in a circle, we know that there are 360 degrees if we go all the way around the circle. 360 degrees. We also can say that we have 2 pi radians in a circle. So since we can equate these two things, 360 and 2 pi radians, if we simply take 360 degrees and divide by 2 pi, which is approximately 6.28, we will get 57.32 degrees. So that is telling us that there are 57.32 degrees in 1 radian. Okay, so how many degrees are in a radian? Approximately 57.3. All right, we will be able to use that to our benefit later. If I wanted to know how far around is pi radians, for example, pi radians is halfway, isn't it? What is that, 180 degrees? Okay, very good. All right, now then, remember we talked about that sine wave graph and what that represented on this circle here? Let's review that. The basic sine function is, and this is the way you would find it expressed in a math book, f of x is equal to sine of x. In other words, I plug in a value of x in terms of radians or degrees, depending upon what mode my calculator is set up for. And that's something else you need to be sure you know how to do too. Okay, and plug that number in here, radians or degrees, and then take the sine of that angle, and then this will give me the functional value, the f of x value for that. Now what that represents is this. Remember, we had a unit circle. This was always 1, and we formed a right triangle by bringing down a line perpendicular to the x-axis. Here's my angle of reference right here, and the length of this side of that triangle is the sine of the angle x. Okay, that's the functional, actually I should say that's the functional value. The x, the number of degrees, is what I'm taking the sine of. Okay, now if I start at 0, the sine is 0. If I go to, let's say, 45 degrees, the sine of 45 degrees, check this in your calculator, is approximately 0.7. So let's put a point there at 45 degrees. 0 degrees, 45 degrees. At 90 degrees, the sine is equal to 1. Check it in your calculator. Add another 45 degrees to the angle. We're coming around the circle. The sine again will be the length of this side of that triangle, will be 0.7 again. Come all the way to 180 degrees, the sine falls back to 0. Now if I can go ahead and connect those dots, can't I? Looking just like a sine wave, isn't it? Comes out of the wall here. Follow that on through. What happens? 0.7 in the negative direction. Negative 0.7. Negative 1. Negative 0.7 again, and back to 0. So that gives me a graph of the sine function, which is like a sine wave coming out of the wall. 60 cycle sine wave. All right. There's a couple of ways we need to express this. Let's say that we needed to know, we had this in degrees, and we needed to know what the value of the voltage was at this point in the cycle. Well, we've got another way to write this expression. We can say that the voltage at some angle theta is equal to the maximum voltage. In this case it was 1, wasn't it? Well, I was working inside a unit circle, times the sine of theta. Now then, that's the most basic form of that expression for finding. I can see this represents a voltage now. And the maximum voltage multiplied by whatever the sine of theta is will give me the voltage at that particular angle. Now then, I could take this sine wave and slide it to the left and slide it to the right. In other words, I could have a phase shift, and we'll learn about that later on too, in which case I need to have a displacement angle to compensate for that. You just call that phi or whatever you want to call it, I don't care. But we would add that to our angle that we have gone through in the cycle, and then take the sine. Okay? So this is the version for finding the voltage at a particular angle. Now there's another version, and that version finds the value of the voltage, the instantaneous voltage value, at some time t after the cycle has started. And that is very similar, V max times the sine of, now here's where we depart, omega t plus or minus some displacement angle. Now then, I'm going to have to do some explanation about what this omega t business means. But these are the three forms that you will run across. These two are the most prevalent, and I would say this one in terms of electronics is the most widely used. We would always, and I need to make a big point of this, we would always need to be in the radians mode on our calculator when we use this one. You need to always be in the radians mode. If you don't know how to put your calculator in the radians mode, you come to us, we'll show you how to do that. All right, here we are back at this formula that we're going to be able to use with our AC calculations. V at any time t of a sinusoidal expression or sinusoidal shaped voltage is equal to the maximum or the peak voltage that you could ever have multiplied times the sine of omega t. Now let's talk about what this omega is. Omega is equal to 2 pi times the frequency of the sine wave. Now what do we mean by, what's the t by the way? The t is time, isn't it? Okay, the t is time, so we don't need to worry about that. We all know what time it is. Okay, so here we go. Omega, that little Greek letter, stands for 2 pi times the frequency. And that turns out to be angular velocity. Okay, angular velocity. What does velocity mean? It's like speed, isn't it? Only it has a direction related to it. Okay, what are we talking about the angular velocity of? We're talking about the angular velocity of, we're rotating around this circle. And that angle is changing. How fast is that angle changing? That is the angular velocity that we're speaking about here. And it is in radians per second. So this works out pretty nicely because I have in my formula here, I have omega t, and that would be radians per second multiplied times seconds, which is for time, right? So radians over seconds, I probably ought to write that out this way. Multiplied times seconds will give me radians left over, and that's the unit I need to take the sine of. Okay? That's what I need to have it in. So that works out very nicely. Now then, let's talk a little bit more about this angular velocity and the radians per second thing. We know we're measuring the angle in terms of radians. One time around the circle is one cycle of my sine wave. Another time around the circle is another time around another cycle of the sine wave. Well, these cycles are happening in some amount of time. That time is referred to the period. The period, reciprocal of the period, is the frequency. Okay? So the unit of time for the period is seconds. The unit for frequency is cycles per second. We call it hertz, don't we? So cycles per second. All right. Now then, if I move that vector around that circle faster, what am I going to have? I'm going to end up with more cycles per second, or a higher angular velocity. Okay, so that's what that means, and that's how that relates to the sine function and relates to rotating around that vector, or that phasor as it's called, around that circle. All right, let's do a little example.